There's some interesting nuclear science news. GE is getting into the small modular reactor game.
Oh, nice. All right, let's get started since we have our review day. So we'll just do some announcements real quick. So of course, I know everybody's still kind of recovering from the snow day. And so just a reminder, right, we will have lab makeups this week. That will continue. And so Tuesday lab people will essentially have our normal lab for Tuesday. So Tuesday lab today with the titration. And on that note, so I forgot to talk about the titration lab. Sorry, let me pull up the lab real quick. So there's never a perfect order to do the lab. Where is this stupid? All right, sorry about that. So there's not a perfect time to do the lab. And so what I mean by that is if you have looked at it or try to work on it, and I did make an announcement about this, but we can't do problem 7 yet. So we haven't gotten there yet in our course content. So I would just hang on to your labs for now, and I may try to cover this after the midterm and show a sneak preview of the math, but I don't want to get into it right before the midterm and confuse people. And so same thing for post. So then that influences 7 and 8. So again, 7, you can't do this yet, so just hang on tight to your labs. Like I said, we'll probably do the math together next week, but we want to focus on our midterm today. And then Thursday, again, will be another makeup day. And it sounds like Friday we might have a little bit of overflow as well for people's schedules. And so Friday I'm putting tentative, but I believe that that's kind of where we're at. I'll probably be at school around 11 a.m. So if you need to do the lab, starting around then or sometime in the afternoon or anything else you need to make up. And the same thing with quizzes. Try to get those done. And if you missed any other quizzes, I think a lot of people were kind of emailing me for that. So yeah, let's just get that sorted soon. All right, let's dive into review. So let's just warm up. Let's start off with these 3 questions. So looking at these molecules with polar interactions, so which ones have polar interactions? 14 is which one have London forces? 15 is which one can form hydrogen bonds? So take a few minutes. before we go over this, so there's a question about the exam. So I'll just briefly talk about the exam format. So, right, well, first quarter, there were way more of you, so I was really trying hard to get a different Gaussian distribution. I'm still going to have, so there's still going to be a mixture of multiple choice questions and free response, but I'm going to do something a little bit different. So I won't do the two portions this time like we did, where we did the closed book multiple choice, took a break, and then did the free response. My only complaint about that is it was just really strange. There were people that would either perform really well in the multiple choice portion and then bomb the free response, or a few people actually did the reverse, which was kind of interesting. So I'm going to try a slightly different approach. So we won't do the break thing, and in that case, right, it will all be open note. But I would still expect it to be time intensive, right? There's going to be more multiple choice questions, and there'll be plenty of free response questions. So it will still be time intensive, but on that note, right, you'll have all your notes from the beginning, whether that's good or bad, right? So kind of figure out now how you need to make your notes, make your study cards, right? So you can quickly flip to the relevant information, or like, you know, again, write out the relevant information. And I don't know how long it's going to be because I'm still writing it. All right, let's go over these. So question 13 here. So which ones are polar? What did you say, Sky? So NF3, Vaughn, do you agree with that?
Yes, and I was also going to say, doesn't CLF exhibit some London dispersion because of the size difference?
Well, they'll have London dispersion, but it's probably still pretty non-polar since they're both pretty electronegative, right? Like if we look at the periodic table, chlorine's right next to fluorine. So yeah, probably just the NF3 there. Questions on this one? And then, so what are London dispersion forces, or London forces? Yeah, Vaughn.
It's a temporary uneven distribution of electrons because of differences in electronegativity, or, yeah.
So we'll say, right, forces from temporary dipoles. And again, right, the key is that everybody has London dispersion, but then which is primarily, right? So probably no dipole-dipole, no hydrogen bonding. So which one would that be? Let's see. Sky, were you? So HCl, though, my only criticism with this one is probably more like polar. So I would probably say that this has dipole-dipole. Since they're a little bit further apart now, right? You have hydrogen on one side, chlorine on the other. But what else is there? Yeah, what'd you say? Helium. Yeah, helium, right? So helium, again, thinking back to, I think we looked at, actually we did look at helium when we did the little example, right? Where we took the snapshot, the two little electrons were on one side, right? So it's primarily dominated by London dispersion. What else? Yeah, chlorine, right? So chlorine, even though, again, individually chlorine is electronegative, the difference is 0. So that's completely nonpolar. So again, dominated by London dispersion. All right, so who can form hydrogen bonds? I'm going to go for one.
CH3OH.
CH, Wait, what'd you say?
CH3OH.
So methanol, and what else?
HF.
Yeah, HF. And again, right, remind yourselves or circle, highlight on your periodic table, right, hydrogen bonding is only when the H is with nitrogen, oxygen, or fluorine. All right, now take a minute or two for 17. So now it wants you to arrange it in boiling point order. So let's start with who do we think is the lowest, or if we're not sure, we could kind of, there's maybe like two options. Let's see. I'm going to start picking on people pretty soon. Yeah, so why would you say that? So I agree with you, but by itself, but also, right, molecular weight is what we want to look at. So it is by itself, but what's the molecular weight of neon? Like, so 20 grams per mole. And then the next one, right, because the only other possibility is maybe ethane, but if we do the molecular weight, so 2 times 12 is 24, so like closer to maybe 30 grams per mole roughly. So exactly, so neon is the lowest. And then I guess we kind of gave it away, right, because this is nonpolar, so that has to be next. This ethane, I'll draw it out. So what comes after our ethane here? Yeah, Vaughn?
Our longer notes are potassium bromide.
So what do we know about ionic solids, though?
They have high melting points.
Yeah, so
Right.
we expect this to be pretty high.
I was just thinking about that. Then it's the longest, our longer correlation.
Yep, so ethanol, and then, right, it does have hydrogen bonding. So we didn't have anything here that was purely dipole-dipole. And by purely dipole-dipole, I mean dipole-dipole and London dispersion. So, right, we didn't have acetone thrown into the mix or something like that, or even formaldehyde. So that wasn't thrown in there because otherwise that would have gone in between. We kind of made a jump. I just felt like they really made a jump from ethane to ethanol, right? Because we've worked with ethanol, and that was closer to 78 degrees Celsius. and hydrogen bonding. So just keep that in mind with ordering, that we could have put something with dipole instead. Like acetone. Yeah.
Even though, what is CH3CH2? What is that?
So this is ethanol, but what we're recognizing, and what I was just trying to point out right now, is that we have one hydrogen bond, right? And so that's the strongest intermolecular force other than, right, the ionic solid. So those are kind of the separate classification. But if we're just talking about molecules, okay, hydrogen bonding is the strongest. And then, like I mentioned, right, there's nothing with the dipole purely. So we just kind of made a leap, right? So these only had the London dispersion or van der Waals. And so here we were just making a molecular weight argument, and then we jumped from this low molecular weight all the way to hydrogen bonding.
And it kind of seems like you can generalize, if you have, let's say, the two options, ethanol and then potassium bromide, and we know that the ionic compounds have a really high melting or boiling point. So we can generally say that even if you see such like a molecule that has a way greater molecular weight, still the ionic compound is going to have a higher boiling point.
Yeah, correct. Yeah, and I probably won't make you do anything of like, potassium bromide versus gold, because that's, harder to puzzle that out of metallic bonding. But yeah, exactly, like other trends. Other things that I could put on the exam. So now let's do another arrange by boiling points. And so we'll have A, 5, so see if you can arrange those. So what are we thinking for this one? So who's the lowest in boiling point? You can just say A, B, C, D, E, or A, B, C, D.
B.
Which one? B? Yeah, so B is in boy. And so yes, right, so just looking at kind of a molecular weight argument. So they all have 5 carbons, but then, right, B would be the lowest since it has the smallest surface area. So then what's next? So C again with the branching, so that's going to lower it. And I wouldn't do anything too crazy with y'all.
I kind of saw that branch is maybe having a dipole moment, or, so what, why, how come A and, because I put A as the second lowest.
Yeah, in this case, since they're all like CHs, remember it goes back to like how well they stack. So the flat chain always has the highest boiling point since they can stack a lot nicer. And any sort of branching lowers it. So that's what I was saying. I won't go too crazy with the branching and make you do like, branch versus branch. But that being said, that's what your future in OCHEM holds. But and then, so after C, what's next? A, so our straight chain. And again, right, they all have the same number of carbons. And then what's our last one? So D. And so I kind of swapped out one of the carbons for an OH. So pretty similar molecular weight still, but obviously the hydrogen bonding would make that higher. So highest boiling point, H bonding. All right, so expect that on your exam, something with boiling points or ordering or which one's the highest, which one's the lowest. Could be worded with vapor pressure. Let's try one of these. So how do we approach our unit cell problems? So we're given the density of silver is 10.5 grams per cubic centimeter at 20 degrees Celsius. They told us it's a face-centered cubics. And so then see if you can calculate. And it's just asking for the length of an edge of a unit cell in this case, so not even asking for the radius. bless you. So walk me through this one. What information do we need? Maybe what cheat sheets are you going to have handy? Yep, so we need to know that. Do you have that handy?
Yeah, 107.1.
So, excellent. And so, right, we said we needed our molecular weight, but then we needed to figure out, right, how many atoms were in our cube and divide that by Avogadro's number to get our mass, right? And we're also thinking, okay, density equals mass over volume. And so what do we remember about the face-centered cube? Or, like I said, right, we can have the right notes pulled up. So thinking about what notes you need, right? Maybe you need this little cheat sheet printed or something. And so face-centered cubic, 4 in the unit cell. So we know to multiply by 4. So going back, so now let's rearrange our equation. So if we want to solve for volume, right, so we want volume is mass over density. And then, so using what y'all told me, so there are 4 atoms in our unit cell. You gave me the molecular weight divided by Avogadro's number, right? Because we're only talking about our unit cell. And then divide by our density, so we're in grams, centimeter cubed. So let me punch this in. All right, so then it looks like I get for our volume 6.8, I'll round it to 3, times 10 to the negative 23rd centimeters cubed. And so then, right, in this case, so we always have to pay attention to what the problem is asking us for. And so in this problem, it doesn't ask for the radius, right? And it only asks for the length of an edge of a unit cell. So all we have to do, right, is take our cube root. But it could have asked us for the radius. And again, if it did, we could go back to our cheat sheet here. And then it says edge length in terms of R, right? So this is equal to L. So, right, you could have set this equal to L once you find it and solve for R. But like I said, the problem wasn't asking for R in this case. Does that make sense for that one? And so going back to the problem, since they just asked for the cube length or of our unit cell, let's take our cube root, if I can plug this in properly. And so then we should get 4.08 times 10 to the negative 8, and I'm still in centimeters. So it didn't ask a specific unit. So.
If you do need to find R, would you divide that by
Divided by, I think it was 2 square root of 2.
Oh,
So yeah, it's 2 times the square root of 2. So yeah, just divide L divided by 2 times the square root of 2. And then that would give you R. Yeah,
and R is not the square root.
correct. Yeah, so I'll just put that, so right, again, if it had asked, so we could have solved for R, and I guess we might as well just punch it in since we're halfway there. And let me just make sure that I'm telling my calculator the proper thing. So R, again, if they had asked for it, looks like 1.44 times 10 to the negative 8 centimeters. But other questions on that one? Yeah, that unit cell is from the notes. The notes should be posted. It says it's up to date. If anybody wants this printed, I could always print it out too. So yeah, in the lab today, if you want to come grab some, and maybe I'll have some extras for the exam, I'll try to print some out since that's helpful. All right, let's keep it moving. Let's try some gas laws things. So try not to overthink 24. Just see what it's asking. So calculate the density of chlorofluorocarbon at 0 degrees Celsius and 1 atm. So before everybody goes off doing a bunch of math, what's this referring to? STP, right? So don't overthink stuff. Don't start, trying to do PV equals nRT and all this crazy stuff. So, right, STP condition, so we know it's 22.4 liters. So then really the only thing we need is the molecular weight. So I don't know if y'all need a few minutes or... Yeah, you have it?
I have it. It is 128.902.
Everybody get that?
Is this the kind of problem where you can find molecular weight by divided by the 22.4 liters?
Define the density, yeah. So we're trying to find density. So yeah, so this is a good review of like what are we asking, and it's okay. All the gases, right, they all have the same volume, but then we're trying to figure out their different densities based on mass. And I thought someone had an answer in the chat. I don't know if they erased it.
I have an answer. Hold
Yep, 5.39, and I see that in the chat. And then we can round up, so 5.40 grams per liter there. Questions on that one? So just think about that for the exam too, right? If it's asking for the density, what is it really asking you to do? Probably find the volume, right, with these gases. And then use, right, the molecular weight to find the density. All right, let's try another type of problem. So one of these partial pressures. So we have 0.513 grams of hydrogen, 16 grams of nitrogen, and they both occupy 10 liters at 20 degrees Celsius. So calculate the partial pressures. So what do we have to do for this one?
Do we have to find the moles for each?
Yeah, so we have to find our moles for each, and then we can probably just use, right, our PV equals nRT. So we want to treat each gas separately for now. You really could have found the total moles of each, but it did ask for them separately. So let's do that. So let's just start off for hydrogen. And so hydrogen's molecular weight of 2 grams per mole. So how many moles of H2 did we get? Yeah, fun.
0.2565.
0.2565. And I think Chet agrees, so moles. And do the same for nitrogen. So let's see, so 16 divided by 20, how many moles is that?
That's 1.15 moles.
1 point?
I got 0.5717.
Yeah, 0.57, and Chat has that, and you said 47.
Yes, that's it. I did my math wrong.
No worries. So just always kind of sanity check yourself along the way. So then we got moles of each. And so again, right now we want to find pressure. So pressure is equal to nRT over V. We have volume, so we have everything, right? T has to be converted to Kelvin. So 293 Kelvin. And then I see answers in the chat for the pressure. So now pressure. R is the 0.0821, of course. All right, so the pressure for nitrogen, do we have, or sorry, what did I do? Hydrogen. Do we have 0.206 ATM for hydrogen? I could plug this into.
How did you get the 0.0821?
That's just the R constant.
Oh,
And then, yeah, it's that constant because we're in ATM, liters, all that. Oh, now I have. So double check my math and your math. So I have 0.617 ATM, but Chat doesn't agree, but
I got
2,
2
that seems high. What do we get?
That's the total pressure I got for the entire system is 1.998. So hydrogen is going to be 0.5999 ppm or 0.6 ppm.
Yeah, because I have 0.6 using our moles. So what other people get?
I got 0.611, so that's something else she's putting under.
Okay, so I wasn't hearing anything close. So 0.611 ATM for hydrogen, or roughly, and then nitrogen, repeat that process. So fulfill all those conditions. And then 1.38 for the partial pressure of nitrogen.
I got 1.39.
Yeah, 38, 39. All right, so that looks good.
Isn't there a way to calculate partial pressures with the whole fractions?
Yeah, so this is not that problem.
Okay. We would have to know the total,
Yeah, you'd have to know the total pressure.
and because we don't, we use the PD equals NRC.
Yeah. So let's see, I don't know if you wanted to, because it's kind of break time. We have another similar problem to kind of the one we did. I don't know if we wanted to do, I was having trouble finding a total partial pressure one. But, so I don't know if you want to work on this before the break or after.
We're gonna do stuff.
All right, yeah, let's take a break then. We'll give people a little break time. And then we can continue with partial pressures or other gas laws.
So I actually I just kind of flying by the seat of my pants because I was able to find the total.
Oh, yeah, but you added them, right? Yeah,
Yeah, mhm.
yeah, because that's the other way to do it.
Yeah, yeah. And that's probably why we got slightly different answers. I'm also using a
Oh,
more
yeah.
citrix in mine.
It's not roasted, that's the difference. It's great.
All right, looks like most people are kind of coming back, so if you just want to start working on 38, you can calculate that one. So what's the key to this problem? How can you approach it? What equation can we use? Yeah, Sky, what are you thinking?
Because they're in vacuum, then is it at STP? Or because they're in,
Well, it gives you all these,
oh, it gives you.
yeah, or at least of them separately. And then, yeah, so they're just connected by a valve. But then, so what's like, how should we treat this normally? What are you
I
thinking?
would start by finding the moles, the total moles of each of the gases separately.
I don't know that we can do that.
Can you use the partial pressures over total, or can you, yeah, the partial pressures over the total pressure to find the mole fraction?
Well, they're separate anyways. But we're still kind of like overthinking the problem. Because remember, we can treat them separately. Yeah, what are you thinking?
Is a P1 V1 equals P2 V2 problem?
Yeah.
You just multiply the, and we have the final volume, because we have both volumes, so it's going to be 1 millimeters. And our only unknown is the second pressure. You know, P1 V1 has to be either 500 milliliters at 732 or 650 milliliters at 825.
Yeah, well, we have, so right, we have the P1s then for these individual cases. So you're on, right, the right track. So we have our P1, right, our V1 for one case. And then, right, we have to do it again. So then, right, our V1, our P1. And so right idea though with the final volume, so that was the key. So kind of, again, thinking back, how do we do this? And so we want to just kind of keep each gas separate. And so that's kind of the idea, right, with this P1, V1. And so we're saying, okay, let's just think about our nitrogen gas, right? So it is in 650 milliliters at 825 torr. And then once we open the valve, again, just treating each gas individually, then we have an extra 500 in volume. Let's get our total volume. And we can be in milliliters, right? That's fine for this equation, as long as we're consistent. So 1,150 milliliters is our final volume. And so now we just have to do them separately. So let's start with N2. So again, right, initially, we have 650 milliliters at 825 torr is equal to, so we need our new pressure and our new volume. So I get my new pressure of nitrogen as 466 roughly. And now let's repeat. So now for oxygen, so we said 500 milliliters at 732 torr. So we need our new pressure. So then I get 318 roughly for O2 partial pressure. And of course we could add them. So then the total mix plus 466. And let's see, looks like Chet has about the same. And so that's the tricky thing, right, is we can't figure out any mole fractions before. Obviously, now that we have the total and their new pressures, right, you could go back and get mole fractions, but yeah, we needed our P1B1 initially just from what we were given. Questions about that one? So let's try a different problem. So now looking at our solutions chapter. And so now we have pepsin is a digestive enzyme. And 3 milligrams of this pepsin were dissolved in enough water to make a 10 milliliter solution. And then the osmotic pressure at 25 degrees Celsius was found to be 0.162 torr. So see if you can calculate the molecular weight. So I'll give y'all a few minutes to start on that. And just to be clear, we should make this clear, right, that this is a non-electrolyte. Just to emphasize, right, that it's not going to disassociate or anything weird like that. So what are we thinking for this problem? What are some formulas that we might need? So which one was that?
That would be, the osmotic pressure I symbol.
Yeah.
I equals RT, and then the fluid polarity symbol, capital M.
So like that? Yep, so that's what we want to use, so that formula. And then, since we said it's a non-electrolyte, we don't have to worry about this I factor. We can just set it to 1. So, right, I equals 1 for non-electrolyte. So that's the only emphasis in these problems when we use that. So now we're molarity RT. And so, right, just remember what the big M stands for. So again, right, I said that was molarity. So moles over liters. All right, so now we're starting to put the puzzle pieces together. And then if I want to use this formula, though, what units do I need to be in for pressure? Oh, what was it? Well, what's the gas constant here? Yeah, ATM.
So you gotta convert toward atmospheres.
Yep, so we need to convert torr to atmosphere, so 0.162 torr. So divided by,
And R constant for 4.
sorry?
Is there an R constant for 4?
There might be.
I think it's in both, but it is not in chapter.
Yeah, I just don't have it readily offhand. And so that's kind of the confusing thing about the R's, right? Is like you could pick another one and be in torr and get the same answer in the end. I don't have that R handy. All right, so let's convert. So 0.162 divided by 760. So that's really small. So I have 2.13 times 10 to the negative 4 ATM is equal to molarity RT then. And so then, right, so now let's think about what we're trying to solve. And so we have this information, so obviously we have a 3 milligram sample. And so right now, of course, right, we have R, we have T, so we're trying to find molarity, right, so we can figure out how many moles that 3 milligrams was, essentially. So that's kind of where we're going. And then divided by 0.0821. Divided by our temperature, so 293, right, converting to Kelvin. Oh, 298, sorry. All right, so then I have a molarity of 8.7 times 10 to the negative 6. So double check me on that. .7. So that's moles over liters. So I just set, oh, yeah. So then, right, molarity is just equal to our osmotic pressure. Yeah. So that gives us our molarity, or our moles, then, right? And so now we're saying we put 3 milligrams and 10 milliliters with our molar solution. So we need to figure out, right, how many moles this was. Because again, right, we put 3 milligrams and 10 milliliters.
0.03 grams per liter.
0.03 grams per liter. So then how can we get to our molecular weight then?
You would flip your molarity, so that you would divide 8.712 times 10 to the negative 6 by 0.3. And that would cross out your liter value.
Yeah, or, so I want to find, so if we have our molarity here, right, then I want to figure out how many moles were in 10 milliliters. So moles times 10, so 0.01. So then we had that many moles in our sample, so 8.712 times 10 to the negative 8 moles in our 10 milliliters, which was 3 milligrams. So now we can finally divide, and then milligrams has to go to grams, so 0.003. So grams divided by our moles. And so, yeah, we should get a molecular weight then of about 34,000. I believe chat got the same. And then, did we get that as well in here? Yes. So then molecular weight is 34,000 roughly. How many sig figs do we have? So 3. So 34,400 roughly grams per mole there. Questions? Because, right, we got our molarity here, but then we had to refigure out, well, how many moles was in our original sample then, right? And we only had 10 mils, so then we multiply that to get our moles divided by mass, or, excuse me, mass divided by moles, and to get our molecular weight. Sorry, which part?
So originally we got 0.03 grams per liter, and then we converted.
Yeah, I just kind of, I think I erased that, or I got confused. Because what I just did is took the molarity and multiplied it by the volume to get the moles that were in 10 mils. Because that's what we needed to figure out, is how many moles we had in the 10 mil sample, but we had our molarity. All right, let's try another type of problem. So kind of skip around. So the other things that you may be asked to do, oops, shouldn't have moved it, would be determine the hybridization at each of the centers. And so, right, I'll just label this 1, 2, 3, 4, right? So determine the hybridization. So SP, SP2, SP3, blah, 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 at each one of those points. All right, so fun fact, anybody know what type of drug this is by any chance? Any guesses? No, you would guess the class by any chance? There's fluorine is somewhat your hint. It's an antidepressant. So this is Lexapro.
That guy.
Which, interesting enough, not to go down a rabbit hole, is actually just the S isomer of this other medication. And so apparently just the S form is Lexapro and more effective. But yeah, just looking at things in terms of drug development too, like you notice fluorines tend to appear. Those are good for crossing the blood-brain barrier and can mimic like methyl groups. Like, for example, Zoloft also has a bunch of fluorine groups, and its real name is like fluorexine or something. And pull it up just while we're talking about fun facts. Yeah. I wanted the Wikipedia picture. No. Yeah, so that's Prozac with the 3 fluorine groups. Anyways, drug design. What do we get for the hybridization at the 1 here?
Got a SP2.
SP2, excellent. What about this one over here? SP. So that was kind of fun, trying to find a compound with this group on there. What about 3? SP3, so right, don't let that trick you. So draw in those hydrogens if you need it, so you're clear that it's SP3. And then what about our nitrogen here? Check again though. Or it's got the lone pair. Yeah, so it should be SP3. And this is not one of those scenarios where I would expect it to be SP2, right, where it could do the donating in that situation. That's a little more advanced, but right, there's no double bond or no conjugation to suggest that this would want to form a bond. Yeah.
So when there's, I don't know all the terminology, but when there's like a, what do you call it? When there's like something stoppable, what are those called?
Like the little hydrocarbon chains, or?
The chain. So when you see the chain, you can assume that there's carbon at each corner.
Yeah.
But then when there's branches reaching out that don't display anything, can you assume that there's hydrogens there, or?
Yeah, so every point is a carbon, right?
Mhm.
And then, you know, carbon has to make 4 bonds, so anything that's not explicitly drawn has to be filled in. So right there has to have a hydrogen. This would be a carbon, which means it has to have 3 hydrogens attached to it. So same thing with like this, right? Like that's a methyl group of CH3 hanging off of it. Same thing here, that's really CH3. They just don't bother showing that.
Okay.
Yeah, and then same thing there, right? You got your joint, so 2 bonds, and then fill it in with hydrogen. So let's try another problem. So I don't know if you've looked on Blackboard, there's this whole exam study guide with practice problems and answers posted. So that's a good resource as well. I wanted to go over one of them. So let's try this benzene one, 22 down here. And it says calculate the heat flow when 13.8 grams of benzene at 10 degrees Celsius is cooled to negative 10 degrees Celsius. And so, right, look at those relevant points, kind of think about when are you going to hit a state change versus when are you just looking at the heat capacity, right? Everything is given to you here. And this is how it would be given on an exam, right? You'll be given the substance. Here are all the relevant thermodynamic values. Go. So I'll let y'all take a few minutes to get started on that.
example in the book that displays like the changing like the critical points? Oh, it's up there. Oh.
Were you just looking for this information?
Yep.
So let's start kind of walking through this. And so kind of right before I would even start diving into the math and anything, I would just identify, again, where our state changes are going to happen. And so, okay, we have a melting point of 5.5 degrees Celsius, a boiling point of 80. Well, that doesn't seem too relevant for 22 at least. And so, right, again, maybe you want to sketch out, so we have 10 degrees Celsius. We need to take it down to 5.5 degrees Celsius. Do our state change. Sorry, I was trying to draw a state change graph. Doing it really poorly. I said to do 22. So looking at 22, so heat capacity, state change at 5.5, and then we have to keep going to -10. So I'm just kind of sketching out, right, my legs essentially. So I'm going to have 3 legs, right? And then you might also want to identify, again, what's the state of matter. So from 10 to 5, it's going to be a liquid, right? So we're going to be wanting to use this liquid heat capacity for that portion. And then, right, state change. So we know vaporization is for gas. So then we need our fusion one. Again, I'm just kind of mapping everything. And then down here it'll be a solid. So we'll need our other heat capacity for a solid. So again, just mapping out our process. And so now we can start doing the math of it. And of course, we have a little complication, right? They couldn't give us our heat capacity and our fusion in the same units, right? We have one in grams per degree Celsius and the others in kcal per mole. So we might as well figure out how many moles we have of benzene. Yeah, so what did you get?
0.1767.
And so just give me the molecular weight first.
Oh, 78.11 grams per mole.
So 78.11 grams.
I didn't know what the molecular weight is, we don't have the formula. Did it say that?
So that is an oversight of this problem. So on an exam, I would have to give you the formula. Yeah, so otherwise you have to know it's C6H6. So on an exam, I'll give you the formula. And then, so sorry, Vaughn, what was the moles again?
It's
1767. Oh, moles. Again, just kind of lining up all the bits and pieces we need. And so now I think we're ready to put, again, our kind of legs together. And I'll label them. So we have 1, 2, and 3. So 1 is just, again, right, the heat capacity. So looking at our heat capacity formula, again, let the formulas dictate what we're doing. So we have the heat capacity for benzene is 0.41 calories per gram degrees Celsius. And this is exactly what we were warning about in a lecture, right? We're also in cals, which I think we've been doing mainly joules before. And so what's my temperature change then?
4.5 Kelvin.
So 4.5, and again, right, just like Vaughn said, so it doesn't matter whether the difference is in Kelvin or Celsius, same. So that's good, right? Just sanity check for everybody. And then grams, so we can directly plug in this 13.8 grams. Oh, sorry, this looks funny how I did it. This is not supposed to be part of the math. So now just calculating the energy for that first leg, so 0.41 times 4.5 times 13.8. So 25 calories for that first leg. So now we can do the second leg, right, the state change. So again, fusion, let me erase my little, so we said that was 2.38 kcals per mole. So just watch the units. So right, maybe we should convert this to kcals later, but just watch that. So 2.38, sorry. So kcals per mole, multiply by the moles we already found. So we set ourselves up for success. So again, that's kcals, or I think I want to be in cals right now, so about 421 calories for our state change. And so then our last bit, right, so we're still at 5 degrees, 5.5, we just did our state change. So now we need to do our last leg. So going from 5.5 to negative 10 degrees Celsius. And Don't forget again, right, different heat capacity now because we're solid. So 0.2 cals, and then right gram degrees Celsius. So multiply by 13.8 grams. And then what's our temperature change? How many degrees? So 15.5. And so then we get 42 calories there. So 42.8 calories. And so then we can just add everything at the end to figure out the total heat now. So again, just watching the units on those. So I just wanted to be in calories. I thought it was easier. You could obviously convert in kcals, doesn't really matter. And so about 488 calories. So I see some thumbs up there. Any questions on that one? So your quiz was pretty similar from last week too. I just don't want to go over it too much because there's a lot of missing quizzes. But again, the same concept, right? So just take each leg at a time, basically. Doing on time. So let's just kind of touch base on the other topics. I had planned to say make an MO diagram for CO as a practice. And so let's just quickly talk about, right, any sort of MO diagram problem. We can take it back to our chapter 9, right, with our cheat sheet. So I think I printed this out for everybody. So you should have, right, your cheat sheet with your order here. And then again, the only thing you're picking is that is there SP mixing or is there not SP mixing, right? So that just dictated the order of our orbitals. And so again, right, you can basically copy one of these diagrams for your exam. So if we go back to this practice problem, so CO would have SP mixing. And so then, right, you can write down your SP mix diagram. So now I'm just going to write the MO diagram. Looking at our valence electrons, so right, obviously we have 4 for carbon, 6 valence electrons, again just looking at the outermost for oxygen. And again, so I could probably do this from memory. I don't expect y'all to. So copy, right, this. So we have our sigma 2s bonding, then our sigma 2s anti-bonding. Then remember with the SP mixing, that puts our pi orbitals in greater overlap since we've essentially created our non-bonding from our mixing. So kind of remembering that. Again, for our purposes, right, we mainly just care about the order. And so this is our sigma formally bonding. But again, right, basically non-bonding. So there's a swap. Don't forget you have to have 8 orbitals total. So 1, 2, 3, 4, 5, 6, 7 for our pi antibonding now. So write px, py. You could call this, right, our p sigma z. And then finally our bad sigma antibonding. So 1, 2, 3, 4, 5, 6, 7, 8 orbitals, right? So again, we mix 8 atomic orbitals to make 8 molecular orbitals. And then we can just fill in our 10 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 there. And so don't forget, write different terms. So that's our HOMO, highest occupied. That's going to be your LUMO then, right, lowest unoccupied. We could start to get into CO, so we're at least appreciating that the electron density is on the outside. And later you'll learn that's how it attaches at the carbon. All right, other things. So I would recommend kind of looking at this study guide. It's good practice. Things that we didn't talk about explicitly that might be on your exam. Sorry, I was trying to find a sample problem. So something like this, right, like either sketching a phase diagram. So I may not have you like sketch it from completely blank, but can you label it, right? Like where's the solid liquid gas line? So looking at that. So I would expect to label that. I think that was that chapter 15, I believe. I was trying to find those triple point diagrams. Maybe that was 16. Yeah, don't forget these terms, right? Isotonic, hypertonic. Now I can't find a phase diagram, but I would be expected that you'll see some phase diagrams. I think it was chapter 15. Make sure you know how to label like the energy diagrams as well. There we go. That's what I was trying to find. So, right, being able to label these for the state changes, understanding that. And then I think we had our phase change diagrams as well in chapter 15. Yeah, the phase diagrams. So, right, solid, liquid, gas, labeling all those points, triple point, critical point out there. So yeah, I would look over that. And then just don't forget your colligative properties, right? That you have your Van Hoff factors, so that was covered in here, right? So don't forget that this breaks into 3 particles, all those good things. So right, again, Van Hoff factor. So I would look at this review. It is helpful. All right, I guess we'll end there. So I'll see you on Thursday for your midterm. Again, it'll be all open note, but it will be probably time intensive, mixture of multiple choice and free response. And then notes should be posted with the review. They should be live and going, but let me know if there are issues. Yeah, for the Tuesday people. Yeah, thank you.
Do we have a makeup?
So Tuesday people will, yes, they'll be essentially having their makeup lab, the regular lab today. Yeah.
I'm not feeling confident with this, the way these are drawn. I think there's an online guy
You got it. It's okay
named
now.
like Organic Chemist. Have you heard of that? Like, do you have any resources that you would recommend for me to specifically practice this? Because it's written a little bit different in the book than what we covered in lecture, and I kind of get turned around with these.
Yeah, I mean, I guess what's the discrepancy or?
Here, this is, so I
That's what
kind of
I did last
understand
year
how to
is
write
that
these
I,
out per the carbon and the oxygen, but then
when I was taking notes,
where
I
the,
would
how they're
print out the
overlapping
blank
here, I'm
sheet,
very
blank OneNote
confused.
with all of their things on it, and then I would follow
And
along
then
and
like
page
being in phase and out of phase and kind of the
and
ordering
doing.
of
Yeah.
that with the SP
And
mixing.
solely handwritten, but I already.
Yeah, because I mean, everything is right here though,
Mhm.
right? Because that's essentially what we did is we kind of copied this, right? Sigma.
So like walking through, I'm looking, starting with carbon, I'm starting with my s orbital, but here it just shows